Okay, so looking at these inequalities, talked about them a little bit yesterday. There's some aspects of these things that you guys obviously, you've been doing them since Algebra 1. Worked on them a little bit last year, Algebra 2. You're going to hear me say over and over, and you've already heard me say it over and over, that a lot of the stuff that we do here is Algebra 2. Okay, what you've already seen in Algebra 2. But I want to make sure that in Algebra 2, I think maybe you learn the process. You learn, do this step, do this step, do this step. But now I want you to know and realize and recognize why you're doing those steps, why that math makes sense, because then it allows you to adjust and adapt when necessary, okay? Because not every question is going to be the same as what we do in class, right? You're seeing sometimes in your homework, questions are a little bit different than maybe what we've done in class. The hope is that you gain an understanding of the concept so that you can adapt and adjust to those things outside of class. That's why I make the questions a little bit different. To make us adapt. I hate in mathematics and science, I hate the monkey see, monkey do concept, okay, or procedure. I've had some issues with students asking about rational equations, okay, and this is actually a linear equation because the denominators are all integer here, okay, so we can factor out a 1/4, a 1/7, and a 1/14, and you'll find out that it's very linear, okay. But if I've got fractions, we like to get rid of them, right?
Yep.
Okay. We need an LCD, correct?
Yep.
Least common denominator. And really all you need is a common denominator. But if I multiply this thing by 56, I'm doing a little bit more than what I need to. Okay. If I multiply by 4 times 7 times 14, whatever that is, 28 times 14, it'll work. Okay. But I'm going to be dealing with numbers that are much bigger than what I need to be working with. Okay, so when we choose an LCD, this is the logic, because this is going to be important. You've already seen it come up a couple times, but if I've got denominators that are variable, okay, remember, variables are just representing numbers, right? Okay, so we want to basically factor all our denominators. So when I factor my denominators here, I get 2 times 2, right? This is 7. This is 2 times 7, right? Okay. Now, anything that's like 2 times 2, I'm going to rewrite with exponents. Okay? So the idea is when I go through and I start deciding what my LCD is going to be, I'm going to pick off the factors that are new. So obviously, as I see this first denominator, that's new, right?
Yep.
So I'm going to look at 2 squared. And then I'm going to sift through all the other factors that I have up there. And I'm going to see if there's anything that has a greater exponent than 2 squared. Does that make sense? For instance, if there was a 2 cubed over here, I would take the 2 cubed because inside 2 cubed is 2 squared, right? Does that make sense? That's why you were told last year you take the one that has the largest power. But why? Well, it's because when we cancel, if I take 8, 2 cubed, it's going to cancel with anything that's like 4. Does that make sense? Okay? So we take the highest power. So 2 squared is going to be taken. 7 is going to be taken. Okay? I get to 2 here. Is that new?
No.
No, that 2 was inside this 4 that we've already taken. Okay? So I don't need to take that one. I don't need to take that one. So 2 squared and 7 are going to be what we use to create our LCD. So our LCD here is going to be 28, right? So I'm going to multiply every one of these things by 28. The only thing you got to be cautious of now, so that would be 7 times 4, right? Is that 28? 7 times 4, and the 4s are what cancel out. So I'm left with 7. Here, I can rewrite the 28 as 4 times 7, and the 7s are what cancel out. And here I can write that as 14 times 2, and the 14s are what cancel out. Does that make sense? Okay. So now, and when I say cancel out, it's because they got 4 over 4. It's a factor of 1. 7 over 7, factor of 1. 14 over 14, factor of 1. So when we cancel out, we're saying they reduce to 1. So now I've got 7 times x plus 5. There's a minus sign right there, and that's going to be important here, because a lot of people will do this work maybe showing a little bit less work than what I'm doing. We get 2 times 1. Okay. So they'll show this. They'll just go straight to 7x plus 35. They'll go minus 4x, and then they'll write minus 16. Because they'll take a 4 that they had here and multiply it by negative 4 and get negative 16, right? What am I really multiplying by at negative 4? Another negative 4, so it should be plus 16. Remember, when you have a negative to a quantity, or subtracting a quantity, you need to subtract all of it, right? Okay, so I need to subtract the x, and I need to subtract the negative 4. All right, that's what we're looking for. So now, simplifying that should be pretty simple from here on out. 3x plus 51 less than or equal to 3x less than or equal to 49, x less than or equal to 49 thirds. Negative 49 thirds. Good call. Negative 49. So then, as we graph that, we're wanting negative 49 thirds there. Now I can be equal to, so is it an open or closed dot?
Closed.
Closed. If you want to use brackets, it's a bracket. Okay. Interval notation, though. This is what I want to kind of revisit. This is why we're talking about these types of inequalities right now. I want to write this in interval notation. So as I take that line right there and I start dragging it to the right, what will be the first number I encounter on this graph? Negative infinity, right?
Yeah.
Okay. And as I continue to drag that, I don't know why I can't click on that thing. As I continue to drag that, what will be the last number I encounter? Negative 49 thirds. Okay. Now you might think, well, that's kind of elementary in regards to like dragging that line. Okay. But when we get to dealing with domains and ranges and some functions here within the next week or so, and then when you get to calculus, you start doing a thing called limits. That kind of wall idea of dragging that segment is going to be very, very, very beneficial to you. Okay? So that's what we're looking for. They're going to ask you this as your answer in WebAssign. Okay? That's what I'll be looking for on tests and quizzes as well.
But they're going to go to the ones where it's like double inequality signs.
Yes, yes.
Shut up, bro.
Are we okay doing those 2 examples? We feel like we've stirred up enough memory from last year and year before on how to do these? Okay. Let's jump to what Blaze is asking about. And they're compound inequalities. Compound meaning multiple, right? Compound word is a word made up of 2 words, right? So compound inequality, inequality made up of 2 inequalities. Okay. Now let's talk about what these words mean. And or. Okay. So and. Remember, is the same as the word intersection. The layman's term for intersection is the overlap. Okay. If we're talking, maybe we're talking about the idea of between. I don't know how you would say between this. I don't know if there's 2 S's there or 2 N's or 1 N. Probably just 1 N. An I.
Yeah.
I'm just going to do this. Between this. And what this means logically, guys, is that solutions that are determined will satisfy all parts of the compound inequality. All solutions will satisfy all parts of the compound inequality. And there's going to be only two parts of compound inequality, so we're going to satisfy both conditions that are established in the compound inequality. So in example 1 there, that's going to be an and statement. So what we find out is that the X will satisfy two ideas inside that example. Okay? The word or, okay, remember the word union? Okay. Okay, now I don't have real great words like overlap or between this or anything like that for or. Okay. But our solutions will satisfy one or the other condition established in the compound inequality. Okay, solutions will satisfy one or the other condition established in the compound inequality. Meaning that when I take an X value and I plug it back in, it might give me a false statement in one of my inequalities, but it's going to give me a true statement in the other one. Does that make sense? It might give me a true statement in my first one, but then give me a false statement in my other one, my second one. Okay, so that's the idea of and or. Okay. Now, when we see an example, okay, like this is the between this idea, okay, because our algebraic component here, that, would you agree that we're establishing the idea on a number line that thing is between -2 and 15, okay? So if it's between, then we're talking an and. This is an intersection statement, okay? What I want to do here real quick is just kind of approach this in a manner that will show us and demonstrate that really when we deal with and statements and or statements, the mathematics is the same. It doesn't really matter whether it's and or or. However, when it's an and statement or between statement like this, we structure things a little bit differently. So it makes people think that we're doing something completely different. We're not, okay? So what I want to do here real quick is just demonstrate what this is saying. This is saying that 2x plus 3 is greater than -2. Would you agree with that? 2x plus 3 is greater than -2. All right. So I get that idea right there. And then I have and the idea that 2x plus 3 is less than or equal to 15, isn't it? That makes sense? So a lot of times we like to read that -2 is less than 2x plus 3 is less than 15. Okay? But if we read it from the middle outward, we say 2x plus 3 is greater than -2 and 2x plus 3 is less than or equal to 15. Anything between -2 and 15 is going to satisfy that and idea. Okay? So now let's look at this purple one. If I were to solve that purple one, what would you do first? Subtract 3. So you get -5 is less than 2x. What would you do over here in this red one? Subtract 3. So I get 2x is less than or equal to 12. What would you do over here then to solve for x in this one? Divide by 2. What are you going to do over here? Divide by 2. Okay, we're going to carry that phrase and all the way through. And if I do, I do the exact same algebra at every single step for both those. Yeah, subtracted 3 and then divided by 2, same thing. Now, when I graph this, what we have to pay attention to is the idea of and. And is an intersection. It's an overlap. So if I go negative 5 halves right there, and I put 6 right there, the way I read this is, you can read this two ways. Negative 5 halves is less than x. So negative 5 halves is going to be smaller than any x value you graph. So negative 5 halves is smaller than any x value that I graph. I can think of it that way, or I can read it from the right to the left, which I think most people are going to prefer. You can say the x values that you're about to graph are greater than negative 5 halves. Either route or interpretation is fine. You get the same result. Now, on the bottom one, it says x is less than or equal to 6. Less than or equal to 6 should be closed in, right? And then we're going to graph that way. Okay? At this juncture, I have to remember that it was an and statement, right? And an and means that I need to pick solutions that work for both conditions. Well, if I think about this solution right here. Choose a number like 10. Say that number right there is 10. If I plug 10 in, okay, I'm going to get, 23 right here in the middle? Is 23 bigger than negative 2? Yes. But at the same time, it needs to be smaller than 15. It doesn't work, right? Okay? So that only satisfied one. We need it to satisfy both. So where it satisfies both is here on the overlap. We're looking at that right there. So we're going to rewrite this then as negative 5 halves is less than x is less than or equal to 6. In interval notation, then, it looks like this. Okay? Now, here's my argument. Why undo the original inequality, the original compound inequality structure, and go through the math, and then at the end have to recompose or restructure my answer into a format that I started with already? Does that make sense? So the argument here is, why not just leave this alone? Because of the idea that I subtracted 3 from both of the original equations or original inequalities that we did on the right there, and then we divided both by 2. Let's just leave this thing alone and work through that all together at once. So if I subtract 3 here, the idea then is I can subtract 3 from all 3 kind of partitions here. So I get negative 5 then is less than 2x is less than 12. Divide by 2, I get negative 5 halves is less than x is less than, is less than or equal to 6. Does that automatically generate the same answer that we had here, that we actually had to do a little bit more work to develop? Does that make sense? Okay. So writing this in interval notation then, I should get the same thing. Most of the time, I think if people were going to do it this way here and graph it, what they're going to write is like negative 5 halves there, they'll write 6 there, and then you won't see two different curves or 2 different graphs. They're just going to do this. Okay? Which, if I think about it, that is exactly the same as what I've got in the yellow over there on the right, the first way we did it. Does that make sense, everybody? So you choose whichever route you want to go. But I want you to understand that when we do and statements, the structure might look different, but you're doing the exact same math that you would do if it was an or statement. It's just then at the last step, when we decide what our answers are and we express our answers, we have to be able to interpret and understand what and means and what or means. Okay? I would venture to say most people are not going to pull apart and write the ands here, but it's fair game. You can do that. All right, so let's do. I don't like how that happened. I'm just going to erase that graph. All right, so now we've got the OR idea. Okay. Well, actually, let's go back real quick. So the idea now, let's choose a number out of that graph, out of that interval, 0. 0, would you agree that's between -5/2 and 6? Plug it in. If I plug 0 in, I get 3 in the middle, right? Is 3 greater than -2? And at the same time, is 3 less than or equal to 15? Okay, so that's what we're looking for. We're looking for those numbers that are between -2 and 15 when we plug our x values in. Okay. So down here in example 2, we've got the word OR. Okay, so here it is structured, and there's no kind of alternative procedure here. You solve this one, and then you're going to solve that one. Okay, so solving that first one, we get 2x is less than what? -4. So x is less than -2. I'm going to have my OR. Here we get 6x is greater than or equal to 0. So x then will be greater than or equal to 0. So again, we're not talking about, we're not splitting atoms here, right? These equations are pretty easy to solve, okay? But it's the logic and the understanding of what our solutions mean that I'm really geared towards here and trying to get us to make sure we understand. So if I've got -2 here, and I've got 0 there, okay? This one says x is less than -2, so we're graphing that way, right? This says x is greater than or equal to 0, so we're graphing that way. Okay? Now the concept is choose any point that you want to that is being graphed here. Choose that point right there. Let's say that is 10. X is 10. Plug that in here. I get 20 minus 7, so I get 13. Is 13 less than or equal to -11? No. Okay? Does not work when x is 10. But it says OR. So I could have met this condition or met this condition. If I plug 10 in here, do I get 64 greater than or equal to 4? Yeah, that works, right? So that's the idea here, is that solution that is being graphed is going to satisfy one or the other equation up there, or inequality up there. Okay? Yes?
I wanted to ask you a question about the homework. It goes over like and or. I just don't know how to put like the.
Let me. We should have a minute at the end, and I'll open it up. Over here, if I choose this number, like -10, -10 is going to say that yes, this one works. -27 is less than -11, but it makes the one on the right, the 6x plus 4, -56 is not greater than or equal to 4, so it makes that one false. Does that make sense? What about these numbers? What about a number like -1? What's that going to do? It's going to make them both false, right?
Yep.
I put -1 in there, I get -9 is less than -11. That's not true. And then I get, what, 10 is, sorry. I don't know. Sometimes this thing just blocks off. So -1. So -1, if I put that in, I get, what, 2 is greater than or equal to 4. And that's false as well, right? Okay, so the points that are not graphed are going to be false in both of them. Now, as a interval notation, what's the first value that I come across if I'm going to take that bar there and start sliding it? Negative infinity. And then what's the next value that I interact with in kind of a unique way? -2. So negative infinity to -2. Okay? And then I'm going to jump some values, right? And the next number that wall is going to interact with would be 0. Okay, now at -2, do I have an open dot or closed dot? Open and open means parenthesis, right? It means exclusion. That's not gonna be an actual solution. I get to 0, and 0 is closed, so it's a bracket, and then the last value I deal with there is going to be infinity. Now, it's the word or, right? So I've got that. Okay. If we come up to this one real quick, just to mention this one here, that there says x is less than negative 5 halves, right? So that would go from negative infinity to negative 5 halves. This says x is less than or equal to 6. So then that would be like negative infinity, to 6. Okay? Now you would not union that. That's an intersection. Does that make sense? But you're never going to write that as an intersection that way because this is showing me that top line, that top graph right there, and this one here is showing me that one. And if I want to intersect them, then the intersection is that, and can't that be written that way instead? Does that make sense? Okay? So when you're doing these, you're not going to use that intersection symbol in your interval notation. Okay? In representing your final answer. Okay? Because if that's the case, if you actually do have these two things intersecting, then tell me what that intersection is. And that's what this here is saying. Let's change this one here to a positive 10. So 3x minus 5 is less than positive 10, or 5x plus 2 is greater than 5. Just write down an example, right? Just as you see it up there. While you're writing that down, do you know what question you were going to ask me about? What assignment?
The 1.8 and 2. I don't know how to type that in.
Okay. We're going to get to that.
I got it wrong. I'll write it down.
All right. All right, so we're looking at here, we got an OR statement. So I'm going to go 3x less than 15, x is less than 5, right? Again, not out, you graduated 5th grade, so you can do that algebra. That's not what we're here, okay? If I go 5x is greater than 3 here, I get x to be greater than, again, 3/5, right? Nothing extraordinary with those two inequalities. What I'm interested in is understanding this. If I say x is less than 5, which would be that stuff there, right? Or x is greater than 3/5, so 3/5 is over here, can I graph that stuff? Okay? Remember what a union means. A union means everything from both, right? You include everything from both. And most our unions we've seen are kind of broken up like that, where there's gaps in between them, right? This one, there's not. This one kind of looks like, if I didn't have that word or in there, it kind of looks like I'm going to be interested in the intersection here, right? Because that's what those graphs usually look like. But because it says or, I want all the solutions from negative infinity up to 5, union everything from 3/5 to positive infinity. And if I write that, I'm wrong. If I write it that way, it's going to tell me, it's probably going to give me feedback. You got the right information, it's just the wrong format. Because when I write it that way, I'm inclined to believe, when I read it, that there are values that should be left out of my number line. Are there any values up there when I say that get left out of my number line? No. So what they want you to rewrite that as is negative infinity to positive infinity. Okay? If you write all real numbers, sometimes it might ask you to actually write the phrase all reals or something like that. Okay? But that's a little bit different, and it's just based off the numbers that showed up in the original example, to where we get overlap of our two conditions, but because they're stuck together with the idea of or, we don't kick anything out here. Okay? Same thing happens. So, and I don't have an example of this right now, but let's say I go through and I've got a graph that uses the word and it looks something like this. So maybe I got like -2 and I got like +5 there. And I look for the and. I look for the overlap. Is there any overlap there with the word and? No. So what's that tell me?
No solutions.
No solutions. Okay. So those are there are occasional situations that might pop up that are different than other types of problems that we do. You might do, 15 questions that are like example 2 and example 1, where you're getting solutions, you're seeing the overlap, or you're seeing the union, and you get 1 or 2 maybe where you're asked for the union, and there's in a graph things overlapping. Or you might be asked for the intersection, and in my graph there's nothing overlapping. Okay, so those are little things, little special case scenarios that we have to be on the lookout for. Okay, so now that's going to get, so if we understand those ideas of compound inequalities, that's the backbone for what I really want to get into, and it is absolute value inequalities. Okay. So again, what does absolute value tell us? Absolute value tells us how far away from 0 we are, right? So if we know what absolute value tells us, how far away from 0 you are, that puts me exactly some distance from 0. Then an inequality tells me I'm either actually to the right of that value, that is away from 0, or I'm to the left of that value, that is away from 0. So I think instead of writing a verbal phrase here in words, let's just write some algebraic phrases here and draw pictures in regards to what an absolute value inequality tells us. First thing I'm going to write is something like this. I'm going to write AX plus B, okay, is less than C. AX plus B, the absolute value of AX plus B is less than C. Yesterday we talked about how we would solve that if that was equals to C, right? You take AX plus B equals C, AX plus B equals the opposite C, and you would solve it, right? That's exactly what you're going to do here. Okay? Now we'll talk about the approach in a little bit and actually the steps. But the steps that we go through will identify that C and that negative C for me. It will give me those positions to the right of 0 and to the left of 0 that we talked about yesterday. Okay? But read that. What that says? It says the distance that AX plus B, whatever that distance is, it's less than C. It's smaller than C. Well, C's right here. Wouldn't a distance like right there be less than distance C? Wouldn't a distance like right there be less than distance C? So what that's saying then is that those distances right there, anything that falls in that yellow is going to be a distance that is less than C units away from 0. Okay? And that's what I would get. I would get that yellow if I just dropped the absolute value bars and solved the inequality. Okay? But because we know distance can actually show up on the left-hand side of 0 as well, would you agree that that distance right there is smaller than c units away from 0? Yes. Would you agree that anything here in the blue is smaller than c units away from 0? Yes. Okay. So when we talk about an absolute value inequality, and it's a less than idea, we're talking about that. Now, here's my question. How would you verbalize these solutions? You would tell me that those solutions are what? Where are they? Where are they located with the information that's up there? For one key word. B. Between. Those two sets of solutions, the blue and the yellow, are between negative C and C, right? So if they're between negative C and C, that's an and statement, is it not? Okay. So this is an and statement. Okay. And I'll give you some rules here in a little bit on how we generate the actual algebra for us to solve. Now, if I say AX plus B is greater than C, okay, there's 0, there's C, there's negative C, okay. If I say the distance of that object AX plus B is bigger than C, it's more than C units away from 0, wouldn't I be talking about those things there? Aren't those more than C units away from 0? What about these on the other side? Are those more than C units away from 0? Okay, so how would I talk about those solutions? I would say my solutions are more to the right of C, and then they are left of C, or left of negative C, right? So I'd say my solutions are to the right of C or to the left of negative C. Does that make sense to everybody? Okay, so this is an or statement. Okay, now we'll come over to the side here, and we're actually going to write down our if-then statement. Okay, so if the absolute value of AX plus B is less than C, so that's an and statement, then to get that between this idea, we're going to take AX plus B is less than C. We're going to take exactly what is inside the inequality. We drop the absolute value bars. But then I'm going to add on to, on the left-hand side, this statement here. The same inequality sign, pointing in the exact same direction, but then I negate C. Okay, so if I start with a less than C, that's what I get. And we'll come back and talk about that again in a moment. Okay, because people start to think that these ideas that I'm going to show you are different. And I need to show you, I want to show you, that they are not different. That says greater than, right? So now the idea, so if I want to get greater than C, then I need to solve the inequality that says AX plus B is greater than C. Okay, and that inequality right there is going to give me this set of blue solutions right here. Does that make sense? But if I want to get this set of blue solutions, that's to the left of negative C, right? That's less than negative C. So to get that set of solutions, I need to take my AX plus B and say that I'm interested in finding values that are left of negative C or smaller than negative C. And I'm going to attach those or stick those together with the word or. Okay? Now, when I do this, think about this. That top one looks like a completely different structure than the bottom one, doesn't it? Okay? Well, let's remember what we talked about in regards to a between this statement. Doesn't a between this statement say, that right there, can I say that all by itself? I can say AX plus B is less than C. That's exactly what I had here, right? Except for I dropped the absolute value bars. Okay? This statement is found by taking, again, AX plus B, flip the inequality symbol, and negate C. But now because it was a between idea, I'm going to write the word and. Okay? Now most people aren't going to do the problems like I just did in that bubble there. Okay? But what I want you to understand is that when you're doing absolute value inequalities, you can remember the phrase, to get both parts, all you have to do is drop the inequality symbol. Or sorry, let me phrase that. Drop the absolute value bars. Drop the absolute value bars. Solve the inequality that is there. Then, rewrite the inequality. Flip the sign and negate the C. And no matter whether it's an and statement or an or statement, you will get everything that you need. And once you get everything that you need, you can then kind of filter out at the end, was it or was it and decide what you need to write your solutions as. Okay? But people think that those are completely different statements, completely different sets of rules. They're really the same. Okay? Now, here's the thing. If you ever see it written this way, people are going to look at that symbol and say, oh, it's a less than, so it's that symbol, so it's that rule. Does this here match the condition set in my if-then statement? No, they have to be like one-to-one. They have to be cut and paste ideas, right? So I need to flip that, use the symmetric property, and it's going to generate this. Okay? So then it's an or statement. So I want to do one of these. Example 2 here. So the absolute value of x minus 3 is less than or equal to 4. Okay? This is an and statement. Oh. So we're looking at C. So if you want to, you can say it's AX plus B is less than or equal to C, and AX plus B is greater than or equal to negative C. But together, all that tells me is negative C is less than or equal to AX plus B is less than or equal to C. I'm always going to write that one. It's faster, it's quicker, it's easier, but it means the same thing as this stuff. So can I just say negative 4 less than or equal to x minus 3 less than or equal to 4? Again, this gets me then to what we've been working on previously, right? Add 3 to all parts. Negative 1 is less than or equal to x, less than or equal to 7. So negative 1, there's 7. We've got inclusion, there's my graph. Interval notation then should be like that. Yes?
So when we do the graph now, we use like the census and stuff with the dot.
It doesn't matter, it's up to you.
Either or, like.
Yeah, either or is fine. Yep. Okay, so I want, just real quick, come down here. I can't apply anything right away, right?
Yep.
I gotta subtract my 1 and divide by 2. So it's going to be x minus 3 is greater than 2, right? So now that's greater than, that's this, ax plus b greater than c. So that's ax plus b greater than c, or ax plus b less than negative c, right? So x minus 3 is greater than 2, or x minus 3 less than negative 2. Again, the math shouldn't be something that we get stuck on, right? The arithmetic shouldn't be something we get stuck on. And we get that, right? Graphing that then, there's 1, there's 5, open dot that way, open dot that way. Interval notation, negative infinity up to 1. 5 to positive infinity. What do I do between them? Union. Okay? Now, to answer your question, Blaze, number 9, or number 2 from the homework, right? I had it here. I don't know where it went. So this here. So this is exactly what we're talking, right? Absolute value of x is less than or equal to 9. So that's our C value, right? So I have absolute value of x less than, so this is going to be negative 9 less than or equal to x less than or equal to 9, right? Okay. Interval notation, we're looking at negative 9 to 9. And that's what they're looking for right there. Okay. Now here, if I go greater than, okay, so that's x is greater or equal to 9, or x is less than or equal to negative 9. So if I were to graph that, there's 9, there's negative 9. We're looking at that stuff and that stuff, right? Yeah. So now we're going negative infinity up to negative 9 to get this portion. Then this portion will be 9 to infinity, and we got to union that.
Okay, can you give me another chance on that?
Yeah, and remember that these have to be chronological. I would not want to write this as 9 to infinity union negative infinity to negative 9, right? That I would not write my number line like that. Okay, so just be careful with that. Okay? Yes? Yep. Say again? There'll be a little factoring on it. Some inequalities. Absolute value equations. I won't put any absolute value inequalities on it because we've only done it for one day. It shouldn't be too terrible. I promise, if you've been breathing in here, you'll be all right.